Hey guys, in this video I'm going to go over quasi-convex and quasi-concave functions, and I'm going to break down the formal definition of these two functions and what that definition means, and hopefully by the end of the video you guys have a very strong understanding of what these two terms mean and the definition that you'll see thrown around for these two things. So before I get into it, I will point out that I've done a video on convex and concave functions. The definition of a quasi-concave and a quasi-convex function will be slightly similar to those. So you want to have a good understanding of a convex and a concave function before you kind of get onto this. So I recommend you check out that video if you don't have a strong understanding of those two things, because the concepts we use, such as linear combination, those concepts, which will be used in this video for these two definitions, for these two concepts, I break down in that video, which I will put a link in the description for that video. So the first thing I'm going to do is just quickly write out this definition, or the two definitions for these two concepts that I will go through in this video. And at first, it's not going to, it might not make sense. There'll be a few things that you're unsure of, but that's okay, because the whole point of this video is that I cover those, and by the end of it, you understand everything perfectly. So the definition for a quasi-convex function will be as follows. So for any lambda within the set or interval 0, 1, a function is quasi-convex if the maximum of f of x, so the function of point x, and f of y, the maximum of these 2 points, is greater than or equal to the function of the linear combination of x and y. So this is what a linear combination is, and as I said, I did go over the linear combination and what that is in the video that I link in the description. But that is a quasi-convex function. This is the definition 1 that we're going to go through. And then for a quasi-concave function, the definition that we're going to go through in this video is as follows. So the function of the linear combination of x and y is greater than or equal to the minimum of function of x and the function of y. Now, as I said, these two definitions, if you're new to the concepts of quasi-convexity and quasi-concavity, these two definitions might not make a lot of sense. And you may have a few questions like, why is it the maximum? Why is it the minimum? Why is it greater than here? Why is the function of the linear combination on this side of the inequality, and so on? And all those will hopefully be answered in this video. So this top definition is quasi-convexity, and this one is quasi-concavity. And I will go through these two definitions in this video, and hopefully by the end of it, everyone here has a strong understanding of these two concepts. So we're going to start by looking at quasi-convexity. Now, before we get into that, let's just forget about everything that we just looked at. Forget about all the notation, forget the previous definitions that I just wrote down. Let's just focus on some graphs. We're just going to draw some lines, because once you understand what a quasi-convex function should look like, roughly, then the definition which encapsulates that will make a lot more sense. So let's cast our minds back to a convex function and what a convex function would look like. So let's just draw a very rough x and y axis here. A convex function will look something like this, or something like this. It's a nice upward sloping U-shaped curve. That's what a convex function looks like. Now, a quasi-convex function, when you think of quasi-convexity, think of a looser form of convexity. It's not as strict. It's not as perfect. It's kind of, as I said, a looser form of convexity. So it would look something like maybe, this. It's not as nice. It's still got that convex shape, but it's just not as kind of well defined as, say, this, which perfectly looks what a convex function should look like. Or this, for example, a quasi-convex function. I'll just draw another quick example. As I said, will look something, kind of like this, or like it's still got it, but it's not as I said, it's not as well defined. It's a looser form of quasi-convexity. Now, what we need to do with this knowledge, knowing that we're still looking at a function that is convex-like and shares a lot of similarities with a convex function, we need to now have a definition that in a way encapsulates convexity but is not as strict as a convex function and not as strict as the definition of a convex function. So that's what our quasi-convex function and the definition for it needs to do. It needs to encapsulate this looser term. It's not as, strict, and it doesn't require as much from the function. There's not as many requirements that have to be met for our definition for a quasi-convex function to work, as in the case of a convex function. So knowing this now and knowing what, these lines and the differences between a convex and a quasi-convex function and the way that they look, once you understand this, I'm now going to kind of go back to the definition and break it down and how this is going to relate to that definition. So now let's take that idea that we just went over of a quasi-convex function being a lesser strict version of a convex function. Let's take that concept and let's try and work towards the definition that was laid out at the beginning, and how can we work towards that? What formal definition for a quasi-convex function makes sense, knowing now what we know, and that it takes convexity and it makes it less strict, and there's not as many requirements that have to be met. How do we translate that into a definition? So the way that the definition that I'm going through in this video, the way the definition does that is by saying, let's take anything that we know that is not quasi-convex and let's exclude that. If we can create a condition that excludes everything that we know is not quasi-convex, then we can have we've created a definition for, or a requirement for, quasi-convexity. So what is a condition that excludes everything that we know is not going to be quasi-convex? Well, first let's just draw a quick example of something that we know is not quasi-convex, and that will be something, say, like this. It goes up and then starts to come down. Again, something that has this cave-like shape that shows some concavity. If we have a function like this, we need to somehow exclude functions like this within our definition for quasiconcavity, because if we have a definition for quasiconcavity and we can somehow have a function like this that doesn't get excluded from that definition, then it's failed. It hasn't done its job. So knowing that, let's write down definition for quasiconvexity, knowing that now. So the maximum of 2 points f of x, f of y, must be greater than or equal to function of the linear combination for any lambda of x and y. Now, let's draw this definition on a graph. So let's take a point here, and let's call this point f of y. And this point, say, on the x-axis was here. And let's take a point x, and we haven't drawn any function yet, but let's say it just correlates to some point on the y-axis through whatever function that we're going to draw, and it correlates to this f of x, and our function looks, something like this, something that you can consider as quasi-convex. So we have our 2 points. That's point x here, point y. There's f of x, and there's f of y. Let's start at the beginning of this definition. The maximum of the 2 points. So we take our two functions, f of x, f of y. What's the highest out of those two? Well, in this case, it's f of y. So that's what this part of our function is. F of y. Now, what is this part? What does this part mean? So this, having a good understanding of what a linear combination is going to be clear, is going to be really important in this, is that for any lambda, we can take the linear combination of x and y, so that would basically mean any point in between x and y. We can take any lambda, or every lambda that you can think of, any combination and different variation of lambda, and when we take the linear combination of that, we're going to end up at some point, any point in between these 2 points, x and y. And the function of that just means, well, let's just take any point in between these 2 points and let's map it onto the y-axis. So it can be anything here. Let's just say, for the sake of it, it's just here, some random point. This is our linear combination. That would be this part within the bracket. When we map that to, should be a straight line, I do apologize. We map that to the function and put it onto the y-axis. That is what this is. So what we've done with this definition and this part of the function within the bracket is this point here. Again, sorry for being so messy. So what we've done with this definition right now is we've made it impossible for any cave-like shape of a line of a function to meet this requirement. That's because if we take any point in between our 2 points, this part here cannot go above this line. So if our function, for example, went like this, and started showing a cave-like shape, or something that is not convex or quasi-convex, it would no longer meet our definition here, because the maximum point of this, so f of y, is no longer greater than or equal to the function of the linear combination, because we could find a point for any lambda. We could find a point right here, this point, for example, and we could map that to the y-axis, and we'd see that this is no longer met. This condition, or this definition for quasi-convexity, is no longer met. So just like that, the key to understanding this definition is just to look at an example that violates it. And once you find an example that violates it, you now understand why this is the definition for something that is quasi-convex. So just to make it absolutely clear, I'm going to shade in the region that would violate this definition for quasi-convexity. So any linear combination that would end up in this yellow shaded area, any linear combination of point x and point y that end up in this area would violate the condition for quasi-convexity. So if our function was like this red line, which we can see just by knowing what a concave function looks like, we know that that's very similar to a concave function. So now that we're wanting quasi-convexity out of this, and we're applying the definition for quasi-convexity, this red line, if the function was this red line, it would fail. This test that we put on it through this definition. So once you understand that, then you kind of imagine it as kind of this upper bound that we can have on our function. And once the function, or if we have any function that goes past that point, past that bound, it immediately starts to violate our definition. Once you think of it like that, the definition for quasiconvexity and quasiconcavity, which I'm about to go on to, are very easy to understand. So if you think of quasiconvexity as having this sort of upper bound on the function that it can't go past a certain point, otherwise it starts to violate the condition, then quasiconcavity is a very, very similar thing. So I'm just going to write now the definition for quasiconcavity. So it's very similar to that of quasi-convex function, except you'll notice that it's kind of been swapped around. So now we say the function of the linear combination of x and y for any lambda is greater than or equal to the minimum of f of x and f of y. Very similar to the quasi-convex condition, except it's almost like the complete opposite. It's now a minimum instead of a maximum, and instead of the, that condition being on this side of the inequality, it's on the other side, and we've swapped it around. And the reason for this is very easy to picture. We are now just doing the exact same as what we just did, except we want to find a condition that excludes any function that starts to exhibit a convex-like shape. And that is the aim of this condition, just as with the previous one. So let's do what we did before and draw a condition that would violate this. And once we find that, then we know why this is the definition and the condition for a quasi-concave function in the first place. So let's draw something that we know is not going to be quasi-convex, because quasi-concave, because this right here, as we know, this is a convex function, so it's not quasi-concave. So our definition now is going to step in and eliminate this. And once you understand how it does that, then you understand, the basic principles and the meaning and the reasoning behind this definition of quasi-concavity. So again, let's just pick a point here, point y, and a point here, point x. And let's map these to, or I might pick x to make it a bit easier to see. Let's take x and let's put it a bit further to the right, further to the left. Let's say here. So it's really obvious what I'm trying to, display. So that's f of x, and this point here would be f of y. So very, very similar to the case of quasi-convexity. Let's take a linear combination. Let's start here at the linear combination. Any point between x and y. Again, let's pick something completely random. Say here. And this, as before, is our point, our condition in the brackets. Let's map that to the y-axis. Again, if you are a bit unsure on the linear combination and how it's used, I do recommend you watch my previous video on this, which I'll link in the description, because understanding this, it's very simple concepts once you get given a few examples. But understanding this as you starting to notice it is very key in understanding quasi-convexity and quasi-concavity and the definitions. So now we've got this part of the inequality, let's move on to this part. So we've drawn our function of the linear combination right here. Now we take the minimum, rather than the maximum, the minimum of f of x and f of y. So of our 2 points that we map, this is always going to be the one at the bottom, the minimum of the two on the y-axis. So this point right here. So our quasi-concave definition states that the function of the linear combination for any lambda has to be greater than or equal to the minimum of f of x, f of y. So any linear combination we take, and the function of that linear combination has to be greater than this point here. So we know in our case here, at this point, with lambda that would take us to here, we do meet that requirement. However, what if we had a lambda that gave us a linear combination of x and y that ended up here. And this would correlate to, say, this point here, just below f of x. Or, in this case, f of x is the minimum of this. So let's just draw this line across here. This is f of x, this line. Again, sorry for not being a bit messy. Now, if you can see this shaded region right here, which again I'm going to draw in yellow similar to before, you'll see that for any lambda that we pick that gives us a linear combination in between here that would take us onto the line that is shaded in this yellow area, we have violated this condition for quasiconcavity. And this function does exactly that, because we know in our minds, looking at this, this is not a concave or quasi-concave function. But how does the definition know that? Well, when we make the definition and the condition, this that we see right here, it's going to eliminate functions like this, because f of x in this case, or the minimum, is greater than any point where the line starts to dip below right here. So as soon as the curve, or as soon as the function starts to exhibit a convex-like shape, this definition keeps those functions out. As soon as you see something like this, it violates the definition for a quasi-concave function. And we're ending up then with a function that's not quasi-concave. And just like that, very similar to the previous case of quasi-convexity, we've got ourselves a definition or a condition that can explain and kind of encapsulate what we're trying to describe when we talk about quasiconvexity and quasiconcavity. In this case, it's just like having a lower bound on our function. As soon as our function dips below a certain point, or the minimum of this dips below that point, it gets violated. Or think of it in a more literal way or practical way. As soon as the function starts to show a shape that is convex, or not the shape that we want it to be, as soon as it starts to show that shape, this condition gets violated. And that's what this yellow area represents. That represents where the function starts to violate this condition, because our minimum point right here is now greater than the function of the linear combination if we picked a point right here, for example. And this condition is violated. And just like that, that is what we mean by quasiconvexity and quasiconcavity.